Okay, for today's homework, we only have two new examples. This goes with homework number 36. Here it says that g is a twice differentiable function. So that means the first derivative and the second derivative exists everywhere. It gives us a couple of points. It says g of 3 is 20. So that's a point, 320. And it says g of 7 is 10. So that gives us a second point right there. What it wants to know is, what is a possible value for g of 11 if these two things are true? Now I want you to notice it says that those two things are true for all x. So you always have the first derivative is less than 0. So what does that mean if the first derivative is less than 0? It means the original function is decreasing. Now if we know that g is always decreasing, then when x is 11, the only thing we know is that the y value is going to have to be less than 10. That's all we know at this point. So this tells us that g is decreasing. Now there is one more piece of information here. It tells us that the second derivative is always positive. So that means concave up. Now if we know that g is decreasing and concave up, then g should look something like this. Now let's go take a look at the two examples of decreasing. Okay, the first example we're going to look at is if you're decreasing by a constant amount every time. So the second derivative would be 0. If you're decreasing by the same amount every time, then when you go right one, you go down the same amount every time. So in this case, that's 1. So right one, down one, right one, down one, right one, down one. So that would be an example if the second derivative was 0. Now here's an example where you're decreasing, but you're concave down. What I want you to notice is that every time we decrease by more. So first we decrease only by 1, then we decrease by 2, then we decrease by 4. So we're decreasing by more every time. So that's what it looks like if your second derivative is negative and your first derivative is also negative. Remember, second derivative being negative means you're concave down. Now we want our second derivative to be positive. So we want concave up. Here's an example of our second derivative being positive. So we're decreasing because that means our first derivative is negative. That's what we wanted. And we also want concave up, so we want our second derivative to be positive. So this is the picture that we're looking for. What I want you to notice is that first we decrease by 4, then we decrease by 2, then we decrease only by 1. So we are decreasing, but we're decreasing by less every time. That's what we're looking for. We want to decrease by less every time. Now over here, if I decrease by the same amount, then when I go right 4, I'm going to go down 10. Right 4, I would be down at 10. So if I decrease by the same amount every time, my third point would be right on the x-axis. But because I'm concave up, I want to decrease by less every time. So the first time I decreased by 10, so the next time I have to decrease by less than 10. So it could be 9 or it could be 8 or something less than 10. So it looks like the only possible answer is going to be C. This was a multiple choice question with only 3 answers. So this one was a little bit tricky. It was like a little puzzle. But because we are decreasing and concave up, we want to look something like this. This is an example of decreasing and concave up. And again, the reason we need to be concave up is because our second derivative is positive. Our second derivative is greater than 0, so that's positive. Okay, this is our last example. Today's practice only has 2 examples total. Here they want us to find the max and min of f of x if f of 1 is 10. So that's going to be our starting point when x is 1, y is 10. Now the graph that they gave us is a graph of f prime. One thing we know about f prime is that when f prime is positive, the original function is increasing. So f prime is positive when you're above the x-axis. We also know that f is decreasing when f prime is negative. Now f prime is negative when the graph is below the x-axis. So that would be down here. One of the things we learned last time is that how much f increases or decreases is based on the area underneath the curve. So let's find the area of each region. Each region is just a triangle. The area of a triangle is 1/2 base times height. So this one is going to be 1/2. The base is 5. You could also do 6 minus 1. And the height is 2. I think you can see that the 1/2 cancels with the 2. And we get an area of 5. Now I'm going to put plus 5. And that's because our original function is increasing on that interval. Over here, you can see the area is just 1/2 because it's just half of a box. No calculation necessary there. I'm going to put plus 1/2 because our original function is increasing from -3 to -2. Now the blue one has an area of 1/2, the base is 3, and the height is 1. So that'd be 3/2, but this one is actually -3/2 because our original function is decreasing on that interval. So we know that our original function goes up 1/2, then down 3/2, and then up 5. So we're going to go ahead and plot those points. The only point we know about is when x is 1 and y is 10. So we're going to have to start there. We know that we go up 5 from x equals 1 to x equals 6. So that means x equals 6 is going to be at 15. So the height here is 15, and the height here is 10. Now we know from -2 to +1, our f prime was negative, so that means our original function was decreasing. We calculated the area to be -3/2, so we know our function decreased by 3/2. So when x was -2, our function was 3/2 higher. 3/2 is like 1.5, so we were 1.5 higher. That puts us at 11.5. We also know from x equals -3 to x equals -2 that our original function increased by 1/2. So that means when x was -3, we were 1/2 lower. So we would be at a height of 11 when x was -3. Now the max and the min has to happen at one of these points. We're basically doing the closed interval test here. You can see that our first derivative was 0 when x was -2 and 1 and 6. So we have to look at those three numbers, but we also have to look at the endpoints. One of those critical numbers was an endpoint. The other one would be -3 for the endpoint. That's where your max or min would occur on a closed interval. We can look at all those heights. Remember, the biggest number is the max and the smallest number is the min. Now our biggest number is going to be 15. It happens when x is 6. So we would say that our max is equal to 15, and it happens when x is 6. The min is going to be your smallest value. Our smallest value is 10. That happens when x is 1. So we can say that the min is equal to 10, and it happens when x is 1. Okay, the important thing to think about in this question is that we did have a point that we knew. We knew when x was 1 that the height was 10. Then we looked at the graph of the derivative, because we know when the derivative is positive, our function is increasing, and when the derivative is negative, our function is decreasing. How much do you increase or decrease? Well, you'd have to calculate the area. Now, these are just straight lines, so the area ends up being just triangles. Later, we're going to get curve shapes, and we'll have to use calculus to figure out the area underneath the curve. But for now, this is just basic geometry. You can find the area underneath the curve because the curve is really just lines, and you just have triangles for the area. Again, we have a derivative that's positive right here. The area underneath that line is 1/2. So that means our function increased by 1/2 from x equals -3 to x equals -2. Over here, our derivative is negative because the graph is below the x-axis. The area under the curve ended up being 3/2. So that means our original function decreased by 3/2 from x equals -2 to x equals 1. Now this last part over here, because those lines are above the x-axis, our derivative will be positive there, and that means our original function is increasing on that interval. So our original function is increasing from x equals 1 to x equals 6, and the amount that it increases is 5 because the area under the curve is 5. Again, this is just a triangle. It's not really curve. It's just straight lines. So we just calculated the area of the triangle, and we got 5. So that means our original function increased by 5 from x equals 1 to x equals 6. Remember, this is a closed interval. So how do you find a max or a min on a closed interval? Well, you just check the value of the original function at the critical numbers and the endpoints. The biggest one is the max and the smallest one is the min. And that's the closed interval test.